يعني لوين it's included.
look هنوقف على linear momentum يعني you are responsible of what was covered until here, okay, with the examples أكيد, and the remaining part is not included, okay?
Yes, thank you, doctor.
Okay. So if you remember, last time we did the following example, and we said that the only difference in this case, we could treat the problem in two ways. We could apply the linear momentum equation with absolute velocities, and we can deal with the relative velocities, and both methods will give us the same result, if you remember. Did we solve it in detail, or we said we'll continue it after? Did we finish this problem together? Do you remember? Okay. So just to remind you what we had. So we have just here a nozzle and the cars that are moving, and the relative velocity at which the nozzle will cross the control, the jet of the nozzle will cross the control volume is V jet minus velocity of the car. Okay. Now we said that at the outlet flux, if we look at it from a fixed frame outside, we'll have a certain inclination. Why? Because relative to the control volume, it will separate into two straight vertical jets like this. Okay. While if we look from outside, we'll see the combination of the relative velocity and the velocity of the car. Okay, so this is VC and this is VC. Okay, and if we want to apply, the question was to find the reactions that should be applied on the car to keep it moving at constant velocity. So if it's moving at constant velocity, then sum of forces acting on it should balance the momentum of the fluxes coming in and getting out. And if you remember, we have developed last time together that sum of forces is equal to sum of if we have 1D flow, this means that the velocity is uniform. Sum of m dot out v out minus sum of m dot n v n. And we mentioned together, okay, that the velocities that can be used here in this equation, whenever the control volume is moving at a constant velocity, we can use for v out, of course, times m dot n. We can use for v out and vn or absolute velocities or relative velocities for both, okay? But of course, when you calculate m dot, always you consider the relative velocity, okay? So if you try to do it here, we'll get exactly the same result. Why? Because look, when you apply along x, okay? Let us take, for example, sum of x equals to the reactions that should be developed along x, okay? Equals to. Now, if you consider the outlet flux for the first case of absolute velocity, for outlet fluxes, these components are vertical, Vg, which represent the relative velocity, and we have seen that the relative velocity is Vg minus Vc. And since the jet will separate into two equal parts of same, but here the area is divided by 2. So if you remember, the area here was A, and the jet will split into two jets of equal area equal to A over 2. Then since we have conservation of mass, the velocity will remain the same, okay? So along y, we don't care for velocities when we apply x relation. So we just have these two ports, this one and this one. Okay. So we have 2 times. So for m dot out, we have 2 times m dot out. Okay. But you know that m dot out is equal to m dot n. So when we say 2 times m dot out, this term represents m dot n. Okay. So we have m dot n times v car times the velocity of the car. Okay. And we have, from this side, we have the inlet. So we should apply, so it's minus. So minus m dot n okay, times the absolute velocity of at the inlet, which is vg. Okay. So as you can see, at the end, the result is if I take m dot n into factor, so sum of x will give me m dot n times vc minus vg. Okay, so keep this result in mind. This was obtained by using the velocities here, v out and v in the linear momentum equation by replacing them by absolute velocities. Let us use now the relative components. So if you look at this case here, okay, if you use relative components at the inlet, the relative velocity is vg minus vc, and at outlets you only see vertical components because your jet relative to the car will split in the vertical direction. So here it's much easier than this case. You will directly get that sum of forces along x equals to the reaction Rx that should be applied should be equal to, here for the outlet fluxes, no velocities along x, so 0. Okay, so it's 0 minus m dot n times the relative velocity at the inlet, which is v jet minus vc. So since you have minus before it, so it's m dot n vc minus vg, which is the same result we got with the absolute velocity. Okay, and for ry also, if you apply for ry for the absolute case, you will see that for the inlet, no y component, and for outlets, your two outlets present opposing velocities, which will cancel out. And the same result you will get it when you deal with the relative velocities. Okay, so whenever you have a control volume moving with constant velocity, you can use in your linear momentum or absolute velocities or relative velocities, and you will get exactly the same result. Okay, any question on this? Oh. Let us do another problem on this. The previous example treated a plate at normal incidence to an incoming flow. In the following figure, plate is parallel to the flow. The stream is not a jet, but a broad river of free stream of uniform velocity u0 along R. The pressure is assumed to be uniform, and so it has no net force on the plate. The plate does not block the flow as in figure 3.10, so that the only effect is due to boundary shear, which was neglected in the previous example. The non-slip condition at the walls brings the fluid there to a halt, and these slowly moving particles retard their neighbors above, so that at the end of the plate there is a significant retarded shear layer or boundary layer of thickness y equals to delta. Now, what we want to do in this problem, look, to summarize and to simplify, we have a flow moving over a fixed wall, okay? what will happen is that initially the flow was uniform. Now, as it will go through over the wall, due to the non-slip condition, particles near the wall will be forced to stay at a velocity of 0. And then this will lead to the development of what is called boundary layer. Okay? And the velocity will progressively increase until reaching again u0 far from the wall. Okay? But since the mass flow rate is constant, okay, because from continuity, if I take any control volume between any two sections in a steady application, I should have that. And here I have an incompressible flow. Okay, I should have m dot n equals to m dot out. Okay, so at any section, the mass flow rate is the same. And in order to have the same mass flow rate, I should have variation of thickness. Why? Because here all velocities are equal to u0, while here I have velocities moving gradually from 0 to u0. This means that I have a region here of lower velocities, and to conserve the mass flow rate, this requires an increase in thickness. Okay? Now my purpose is to get an expression for this thickness using the concept of continuity. This is the idea. Okay, so first they want me to find the drag force acting on my fluid. Okay, yani the force acting from the plate on the fluid, and I want to find this function of rho, u0, delta, and the plate dimensions R&D. Please, in such problems, always think of applying both continuity equation and linear momentum equation. So these are the main two applications for Reynolds transfer theorem we have covered until now. And this is the application that you are responsible for this exam. Okay, so you should just always think about combining both, because to calculate a force, you need to know the velocity profiles. So what you are interested in, you want to get the total drag force exerted by the wall on your fluid. Okay, so we want to find, of course, this is an action reaction. And if they ask you for the drag force on the fluid, it will be, you will get your result to the left because the fluid is moving to the right. So the wall will try to oppose its motion. And by action reaction, if they want you to find the force of the fluid on the wall, then when you find this force, you say that the fluid will exert on the wall an opposite force, but equal in magnitude. Okay? So to find this drag force, we need to consider the control volume of the fluid. Okay? And this is, you can take the control volume containing the fluid, and of course here it should not contain the plate. It should be to be accurate, the boundary should be here. Okay, because you want to get the interaction force between, so it's just the line. So let us draw it by a straight line. It's just this line, at the contact with the wall, without including the wall with us. Okay, so this is our control volume, and this control, if we neglect the weight of the, even if you don't, the weight is in which direction? In the vertical, and you will have normal opposing it. So we don't care for forces in y, motion is along x, so we will write our linear momentum relation along x. Okay, so along x, what do we have? We have the drag force of the exerted by the wall on the fluid. Now we have P atmospheric outside. Okay, so we have, since the fluid is subjected to the atmospheric pressure everywhere, so the action of P atmospheric will cancel out. So we just have the drag force along x. Okay, now if you want to apply the linear momentum relation to get F drag, we should consider inlets and outlets. So here we have one inlet at section 1, and it's a uniform inlet of velocity u0. And we have an outlet at section 2, but what is challenging about this outlet is that the velocity is changing. It's not a constant. So we have a certain profile for velocity, okay? And in order to be able to get the momentum flux at the outlet, we need to get u function of y and integrate it, okay? There. Now, how to do this? At this stage, I told you they will give you the profile of velocity. You are not responsible of knowing how to get the profile, but you will be responsible of finding the thickness delta. The thickness delta, you will obtain it from continuity equation. So by applying that m dot n equal m dot out, you will be able to relate delta to the initial height h. Okay, let us see how. So first, concerning the first step in such problem is to determine what is our control volume. So here they are defining the control volume, okay? And they are saying they are looking at inlets and outlets. So as we said, if you look at the figure, along only you have a crossing flow along from 0 to 1 and from here at edge 3, okay? Why? Because here at this level, this line, you selected your control volume in a smart way, such that this line is a streamline outside of the shear layer region. Why we did this? Because you know that when you take the line of your control volume as a streamline, the fluid along this line is tangent to the streamline. So velocities will not be able to cross the control volume, and this will simplify your analysis because here you will not have a crossing flow. And of course, at this level, zero velocity, no crossing flow. So you only have crossing flow at this level and at this level. So this was a smart choice by just considering a certain streamline outside of the shear layer region where the flow is uniform. So now you are sure that the whole boundary layer is included inside your system, okay? And the importance of this is that here at the extremity of your boundary layer, you have that m dot n here is equal to m dot at this level, okay? So here it's just the end of the boundary layer at this point here. The point you are considering here is a point of the boundary layer. So we can say that this flux here will be equal to this one, okay? Now, second step, okay? We will start to write our equations, okay? We'll start by the linear momentum equation because we are interested into getting the value of the drag force, okay? So as we said, we apply linear momentum along x. This will give us minus d, which is because the drag force is applied on the fluid is to the left, equals to. We should perform linear momentum fluxes on inlet and out, okay? Now, why we will write first the form in a general integral way, because as I told you here, you have one, the inlet is uniform, but the outlet is not. So let us start by writing the general relation. So over the inlet, I can write that the flux is rho integral over section 1 of uv dot n dA. And we know that for an inlet, okay, v dot n is negative. Now, since for the inlet u is constant, I can just replace u by u0. And v dot n, so you know this is the inlet, this is v is equal to u0, and n is opposite. So when you do v dot n, you will get minus u0. Okay, So v dot n will give you minus u0. Now, what is dA, the elementary area we are working on? Let us go back to our figure. Okay, this is your inlet. You are integrating over the vertical direction. Okay, so here your elementary area will be a small thickness, and since this is in the vertical direction, we'll call it dy, times the thickness perpendicular to the paper. The thickness perpendicular to the paper is the plate of width b. So dA is dy times b. This will give you the elementary area we are working on. And now you will integrate between 0, because your flow is starting from here, to h. Okay? For the outlet, we will perform the same operation, but the integration will be from 0 to delta. And delta is different than h, and we want to try to relate them, and we'll see how. Okay? So now we can say that for the inlet, since u0 is constant, when we put integral rho u0 times v dot n is minus u0 times b, okay? Since all of these are constants times dy, then we can take them outside of the integration, and the result will be minus rho u0 squared times b times dy. Okay? While for the outlet, times integral dy. And what is integral dy between 0 and h? It's equal to h. So I can replace integral dy by h. Okay? Now for the outlet, it's more complex. Why? Because u is function of y. So if you do for the outlet the same procedure, you will get now a plus, because v dot n at the outlet is positive. You will get plus integral rho times u. Now v dot n is equal to u again, so u squared, okay, times b dy. Now b and y are rho and b are constants. You can take them outside of the integral, but for you cannot do it. For you should keep it inside of the integral, and you will integrate from 0 to delta. And to be able to continue, they should tell you how is the profile u function of y. Okay, so they should give you the form of this profile to be able to proceed. Okay, let us see here. They will give us a profile and we'll use it to continue. Okay, so as we said, when we integrate for the inlet, since u is constant, it will, u0 is constant, we'll take it outside of the integral, and we'll get minus rho u0 square bh. And for the outlet, we just keep u inside, okay? And then what will happen is that we can obtain an expression for the drag force by just taking, because here you have minus d, so to get plus d, you do plus rho u0 square bh minus rho b integral from 0 to delta of u squared dy. Okay, now the next step is to say how to compute this term. Okay, so to do this, we need, as I told you, we need the velocity profile. Now I will give us a profile and we'll work on it. But before, as I told you, we don't know what is delta. We should try to think to relate delta and h. To be able to relate delta and h, we should use the continuity equation, which was not used yet. Okay, how to use the continuity equation? All I have to say is that m dot n is equal to m dot out. Okay, and what is the expression of m dot? So if you apply integral over the control surface of v dot n dA, we have, this is minus m dot n integral ub dy times rho. Okay, and since u0 and b are constant, you can take them outside of the integral. So you will get the first term will be minus rho times U0 times B times H, which is rho VA. Okay, this is the expression of a mass flow rate. Plus, for the outlet, rho and B are constant, but U is variable. So plus rho B integral from 0 to delta of U dy. This relation will allow you to get delta function of H, and we'll see how with a numerical example. Okay, so now to be able, we cannot continue if they don't give us the profile. Okay, so all we can do if they don't give it, if they don't give us the profile, all we can do is to stop here at this level. To be able to get a solution, they should give us the profile of U. This is what they did here. They said that U can be approximated by the following profile: U0 times 2y over delta minus y square over delta square. Okay, so now all we have to do is just to apply. Let us find delta together. Okay, we said that to find delta, what is the equation to use? From continuity, we got that rho times U0 times B times H, which is the value of m dot n, is equal to rho times B times integral from 0 to delta of U dy. Let us replace U by its formula. So you have U0 times 2y over delta. Here what they did a change of variable. So they considered that y over delta is our variable. You can do this, you know, it's just a mathematical tool, but at the end you will get exactly the same result. This will simplify a little bit your formulation, because as you can see, you have y over delta, the term is repeating here and here. So here you have y over delta, here you have y over delta square. So instead of integrating with respect to y, what you can do, you say if I put n equals to y over delta, okay, then I can express dn. So dn will be then equal to dy over delta. Okay, delta is a constant. So then I can replace dy. So I can replace dy in my expression. I can do change of variable and replace the dy by delta times dn. Okay, and then what will happen then is that instead of integrating from 0 to delta, I'll integrate from 0 to 1, and I will get the following. This is equal to rho times b times delta times, also U0 is constant, I can take it outside, times U0 times integral times b, of course, equals to integral from 0 to 1 of 2. So instead of y over delta, I put n, so 2n minus n square dn. Okay, so look here, first rho will simplify, U0 will simplify, b will simplify. I will just have a relation between delta and h. If you integrate this result, you get that h over delta is equal to integral of 2n is 2n square over 2, which is n square. Okay, and integral of n square is minus n3 over 3. So minus n3 over 3 between 0 and 1. Now, if you replace by your boundaries, you get 1 minus 1 over 3 equals to 2 over 3. So you can deduce that delta is equal, in this example, is equal to 1.5 times h. And this is how, from continuity relation, we were able to determine the thickness at the outlet of your boundary layer. And once you determine delta to get F, now you go back to your expression and you do the same procedure to integrate. You let n equal to y over delta, and then you can get the drag force, the expression of the drag force. And as you can see, your drag force will be proportional to rho, u0, b, and w. Okay. Any question on this problem? Okay. So this is what you are responsible for this chapter. Okay. So for the exam, you just have this part. You don't have the part that will continue now. Okay. So if you want, I will continue from here. But for the exam, you are only responsible of continuity equation and linear moment. Okay. Any question on the problems before we continue? Okay. So we have seen together that the Reynolds transport theorem has a variety of applications. The first one is by replacing B by 1, we get the continuity. The second one is by replacing B by V, we get the linear momentum equation. And now we will see that if we set the energy E as variable, this is the energy of a particle of a fluid, okay, and this energy will include potential, kinetic, and internal energy, okay. Then we will obtain the second law of the first law of thermodynamics for a system, which states that the rate of increase of the total stored energy of a system is equal to the net time rate of energy addition by heat transfer plus the net rate of energy addition by work transfer to the system. Okay, so this is what we should know. We should know that if we apply the Reynolds transport theorem on this variable, then we'll end up with the following relation, that the variation of energy of the system is equal to summation of all fluxes coming in of energy and work minus all fluxes getting out. Okay, so and this is logical because if we supply heat to a system, its energy will increase. If the system produces work, its energy will decrease. So everything coming inside the system as energy and work will increase the internal energy of the stored energy of the system, and everything going out will reduce this energy. Okay. So let us of course, we will not go deep into thermodynamics, so because it's a fluid course, but just I want you to see the importance of the Reynolds transport theorem and how many applications it has. So for thermodynamic applications, they will be simple. Okay, so you will have, let's say, a turbine, a pump. Just you should know that if I have, for example, for the pump, I should supply work, so W dot N. Okay, I should do plus W dot because I'm supplying work. While for a turbine, it's producing work, so it's minus W dot. Okay, so that's it. Now, concerning the work can be in several forms. Okay, so the power transfer can be in form of the, let's say you have a piston displacement, so it can be of translational work, or it can be rotational work. So if you have a shaft, and in general, this is one of the main application because when we have turbines or something like this, then we have rotation. So in case it's related to shaft torque, then it can be expressed as the shaft torque times the angular velocity of the shaft. So for example, we might ask you, if you have a thermodynamic application, we apply the energy law, you got a W dot from the energy law, and then you can deduce, if you know the couple transmitted, what will be the angular velocity of the shaft. Okay. Now, concerning for work, you have, as we said, you have several types of work. One of them is the work transferred to a shaft. You have work of all forces acting on your system. So you know that from dynamics, for a force to do a work, it should have a component along velocity. Okay. So if you want to get, for